Okay, that video, ow, jeez. So I was gonna say that I did not get around to, scheduling the new problem session. And I also, I think there was some miscommunication. I'm not sure if the first problem session was even available.
Yeah, the TA did not show up to that one.
Yeah, so I'm sorry about that.
Yeah, he emailed to me that he couldn't make it that day later.
Right, yeah. So yeah, I wasn't aware that that was going to happen. So um I don't know what to do this week since we're like basically at the end. I think maybe I'll just like roll some of the problems over to next week and have you guys work on like maybe a little bit longer set of problems for next week, or I could just post solutions for those. um Okay, and you can always stop by my office hours if you want to go over those with me. And if you can't make my office hours, you can always schedule a time to meet with me because I'm pretty flexible with that. I usually have like Tuesdays open to meet with students. So, okay, so let me get this up here. Oh, crap. Okay, co-host. Okay. So there was some stuff I wanted to clarify from last time before we move on. So I'm just gonna go over that first. Let's see. Here we go. Okay, cool. Great. Um, which one was it? Okay, this guy right here. Okay, so at the end we were talking about finding the null space and column space. I did want to say something here. So this is like a small but important thing. So I gave this example where I said, okay, say this matrix row reduces to this particular matrix here, given here. I actually want to say that it's equal to. So since I want to, there is actually a distinction between what the column space will be if we start with this matrix and what it will be if we start with a different matrix and then we row reduce it to this. So that is important. I will say that, okay, so given this, we do get that this is the answer. So it's just the span of the original columns where we had pivots. And it just so happens that our matrix was already row reduced. So the pivots were, or the, how do I want to say this? Basically, we don't have to revert to the original matrix because this is our original matrix. So hopefully that's clear. I'm also going to do the last example, so maybe it'll be more clear after I do that one as well. Okay, so great. Determining the null space and column space. So we went through number one. It was great. So I'm not going to talk about that one. For number two, I did say like there's another way you can do this, which is more standard. So I just wanted to go over that as well. So here we do want to, so we're looking at this equation. We want to solve this. We get that x plus 2y plus 3z equals 0. If we move these guys to the other side, notice that y and z are both free variables, right? So we're just moving our three free variables to the other side to write x in terms of those free variables. And then I guess we can say y and z are free. And if we want to write this in our parametric vector form, what we do is our solution will be x, y, z. I'm reusing x, unfortunately, but that's fine. we just replace x with our formula that we got here, and then we have y and z, and we can split this into two vectors, one corresponding to the y's, so -2, 1, 0, and one corresponding to the z's, so -3, 0, 1, right? And then your null space of A is, if you want to write it as a span of vectors, it's the span of -2, 1, 0, and -3, 0, 1. Okay, so the span of two vectors, remember, since these are linearly independent, this will form a plane in R3, right? So if you think about all of the possible linear combinations of two vectors, that will form a plane. We also, when we write it like this, can see that this gives us the equation of a plane in R3. So both ways we can see that. And then the column space was just R, right? So but that part we already finished. And then let's go through this last example. So again, we're trying to find the null space and column space. So let's start by row reducing this matrix. So I started with this guy up here, and I didn't copy down the matrix, but the first step that I did was multiply the top row by -1 to get a 1 in that first position, right? So just continuing on with this row reducing, what we would want to do is take row 2 to row 2 minus 2 times row 1, and we should get a 0 there. We'll get +4 plus 3, so 7. We'll then get -6 plus 8, -8, so that's -14. And then in the last thing, we get -16 plus 5, which is, or -5, which is -21, right? Okay, so luckily everything in the second row is divisible by 7, so we can just divide through and make it look a lot simpler. So we've got the same first row. Second row will now be 1, -2, -3. And then to get it in reduced row echelon form, we just want to clear this -2. So we can do that by taking row 1, 2, row 1 plus 2 times row 2, right? Okay, so we should end up with this. Our second row will not be changing. And then our first row, we'll get 3 minus 4, so -1. And then we'll get 8 minus 6, so 2. Okay, so what do we know about the column space? Right? So we have two pivots, right? So pivots in the first two columns. And so our pivot columns from the original matrix, right, are going to be the first two columns in the original matrix. So that was this guy up here. Sorry, it's so far away. So it's going to be this first column and this second column. So it's -1, 2, -1, 2, and 2, 3. So instead of taking the columns from the reduced row echelon form, we're taking them from the original matrix, but they're going to correspond to the same columns, right? That makes sense?
Wait, so the column space does not include like all of the columns of the matrix A?
It does, but we're finding sort of the minimal spanning set, right? We could just include all of the columns, but it turns out that these two are unnecessary. So we are finding the column space. What we're actually doing is a little bit more, we're finding a basis for the column space, right? So a non-redundant spanning set, right?
Do we also know that since there's a pivot in every row, the columns of A span R2?
It is, since there's a pivot in every column, the columns of a span are 2.
Oh, okay. I thought that the spanning came from the row.
The spanning of the image corresponds to the columns.
Okay,
Is there a
thank
pivot
you.
in every column?
What's that?
Is there a pivot in every column of that matrix?
There is not. Oh, I see. Okay, maybe I'm incorrect. There's a, okay, the spanning, sorry, what did you say again? You said if there's a pivot in every row, then you get, yeah, okay, yeah, you are correct with that. Sorry. Pair theorem 4. Is that the invertible matrix theorem?
No, it's from like way back in chapter 1.
Okay.
It says that the following statements are equivalent, that A has a pivot position in every row and the columns of A span RM.
Right. Yeah. Okay. You are correct about that. Yeah. So
Okay.
sorry.
No, all good.
Okay. So let's see. Was I saying? Okay.
So,
Oh, another question?
yeah, so the basis for a column space is basically the columns where where there's a pivot position, right?
Yeah, exactly. Yeah. So for us, so the column space is the span of those first 2 vectors in our matrix, which again are -1, 2, and 2, 3.
Is there a preference between saying that the column of col A equals span of those vectors or equals R2?
So, right, you could say, yeah, the column, yeah, you could say R2.
Is there like a preferred way to do it?
I would say this first way is better because it's going to work in more circumstances, right? So it might not span all of R2, it might be some subset, but you can write it this way. And then you could notice, oh, that's all of R2. So you just write R2. Right?
Okay, but it's not incorrect
It's
to
not
say that it's
either.
okay.
Yeah.
It hurts my head because I'm used to the idea that you have to get it down to like a certain form for it to be correct. But like here, you can just write it a bunch of different ways.
Yeah, I see. Right. Yeah. I think this first way is probably best. Right. Okay, so this is the column space. The null space, remember, is just the solutions of the equation AX equals 0. So we're just going to write down the solutions in parametric vector form, and then that will tell us the spanning set for our null space. So we have the row reduced form, which tells us that x1 is equal to x3 minus 2 times x4, and x2 is equal to 2x3 plus 3x4. Okay, and then our free variables are x3 and x4. So a solution will look like a vector in R4, where the first 2 coordinates we can just replace with these equations that we got, and then we have x3 and x4. And then, so this is just the process we've been doing for a while now. We just pull out that x3, create a vector for x3, and another one for x4. So those are our 2 free variables. 3, 0, 1. There we go. Okay, meaning that the solutions are going to be the span of these two vectors. So 1, 2, 1, 0, and -2, 3, 0, 1. Okay. Okay. So, great. This is basically what I wanted to finish up from last time. And I will go ahead and update the notes since this is from the notes that I had for Monday. So I'm just going to update these, and if you want to reference them, you'll find them under Monday's materials. But now let's move on to well, what we're going to cover today. So I wanted to talk a little bit more about bases. So bases, this is plural for basis. Right. So first of all, sorry, 1 second. Let's just review the definition, right? So I am going to start using this notation. It's like a cursive B or a script B. And that will just be the set containing these vectors that will form a basis. So we say that this collection right here is a basis for a subspace H if, does anybody remember one of the conditions?
I think the set of vectors are linearly independent.
Yeah. So if this collection V1 up to Vk is linearly independent, and what else? Has to do with the span, right? H equals what?
H equals the span of the vector.
Exactly, yes. H equals the span of these guys. There we go. Okay, so this is our definition. We went over this last time, but it's good to just try to remember it off the top of our heads. Okay, so about bases, we already said that they were not unique, right? But we can actually say more than that. It's any non-zero subspace has infinitely many bases. So not only is it not unique, it's very not unique. But there is something that they all have in common, and that is the number of vectors that will be in a given basis, a basis for a given space, that is. So any non-zero subspace has infinitely many bases. But any basis for a given subspace, so if we're looking at one subspace and considering all of the bases that we might have for it, they will all have, I'll say subspace H, they'll all have the same number of vectors. Okay. So we talked about the example of R2, which is spanned by the two vectors 1, 0 and 0, 1. And we also said that it is spanned by, let's see, 1, 0 and 1, 1. And both of these are examples of bases because they both are sets of linearly independent vectors, right?
So here the subspace is R2.
Yeah, so we're just saying R2 is a subspace of R2. Right. So it's a sort of trivial subspace, but yeah. So and any basis of R2. So let me save this. Both are bases. And any basis of R2 will have two vectors. I mean, first of all, it can't have one vector because that will not span all of R2, right? It will only span a line in R2. And then,
Right.
so if we have three vectors, we know that one of them can be written as a linear combination of the other two, making that collection not linearly independent. So we have to have two vectors to span R2.
So like if we add a third vector, then one of them will can be written as the other two. Okay.
Right, so one of them can be written as a linear combination of the other two. Okay, and in fact, R2, or let me say it this way, any pair of non-collinear, I'm gonna put it, okay, put non-collinear vectors in R2 form a basis of R2. And so in this case, it is clear that we have infinitely many possibilities for a basis of R2, right? We just pick any two non-collinear vectors, and there are infinitely many pairs of non-collinear vectors, right? Okay. So there is one basis that is important. So this is going to be, so Rn, so considering Rn, this has a natural basis, right? And it's just where we take all of those coordinate vectors, E1. So this is where we have just one in the first coordinate and zeros everywhere else, right? E2, where it moves to the second coordinate. So we have 0, 1, and then zeros everywhere else, and so on up to En. So these vectors, we talked about these before. These are called coordinate vectors. And it's not too hard to see that they form a basis of Rn, right? You could see how you could write any vector as a linear combination of these guys and that they would span the whole space, right? And they're linearly independent. So if we take the collection, E1, include E2 up to En, this forms a basis of Rn, which we will call the standard basis. Okay. And then, so this is kind of nice because we can think of like a vector in Rn, or let's say R3. So say we take a vector x equals 1, 2, 3. And the reason why we call these coordinate vectors is that we just split these. We can split this into 3 vectors, right? Where we just keep one of the coordinates in each vector. So I've split it this way. And then I can write this as E1 plus 2 times E2 plus 3 times E3, right? So writing this, so writing x as a linear combination of these coordinate vectors actually tells us what the coordinates are going to be, right? Because this 2 corresponds to E2, which tells us that 2 is the second coordinate of x, right? Okay, so we can actually use this idea, but for other bases as well, right? So there's going to be this notion of a basis as a coordinate system, right? So this is our standard coordinate system, but we could also use a different coordinate system. So we can actually interpret any basis as a coordinate system. And this comes from the fact that there's a unique way to write, given a basis, there's a unique way to write each vector in that subspace that the basis is for, right? So given, so this is just setting this up, given a basis, let's say B with some vectors for a subspace H. And so we have these two things, and we have a vector x that is in the subspace H. There is a unique way to write x as a linear combination of those v1 up to vk. Of the i's from our basis. So right, we can write x as c1 times v1 plus c2 times v2 plus ck times vk, right? Okay, so because all of our, we have no redundancy in our bases because they're all linearly independent, that means that this representation is unique.
So like, yeah, because like there's only, for any x vector in H, there's only one way to write it as a linear combination of the vectors in the basis.
Mm-hmm. Yeah, exactly. It's not too hard to prove, but I was going to skip over that unless you guys are interested in seeing like the quick proof. What do you guys think? Yes or no? It's also in the textbook, so you can look it up.
You said something. Oh, sorry.
No, I was just saying, I don't mind you going through it. I mean, even though it's in the textbook, it's nice to see it written out and explained.
Okay, yeah, no problem. And Veronica, did you have a comment?
Yeah, you said something about like redundancies. I was curious what that was.
Okay, so when I say redundancy, I'm sort of like speaking loosely, but I just mean that when we have a collection of linearly independent vectors, there's no way that we can write one of these vectors as a linear combination of the others. So that's what I mean by not having redundancy. If these were linearly dependent, this collection, then it would have some sort of redundancy.
Okay, that's what you mean. Thank you.
Yeah. Okay, so let's go over that real quick. So the idea is we want to say that this representation is unique. So let's just suppose that it's not unique. So this is just quick proof. So suppose that this representation is not unique. Then we can write X as this linear combination of the VI's. So using the constant C1 up to CK, and we can also write it using different constants. So say D1 times V1 up to DK times VK, right? Okay, so we have that these both of these things are equal to X. So if I write, so if I take the first thing, C1 times V1 up to CK times VK, and I subtract the second representation, which was D1 times, oops, V1. Wait, okay, V1 up to DK times VK, like that. So if I subtract those two things, that's the same as subtracting X from itself, right? Because those are both representations of X. X being the same as itself, we just get the 0 vector on that side. And then on the other side, we can just group these by the vectors. So by that I mean, like, I'll group the first term of each of these. So we get C1 minus D1 times the first vector V1 up to CK minus DK times VK. So for each of those vectors, we get C minus D. Ci minus di, that is. Okay, but since this is equal to the 0 vector, that means that each of these coordinates has to be 0, right? So each of those constants out front. So that means that C1 minus D1 equals 0, C2 minus D2 equals 0, and CK minus DK equals 0, meaning that our supposed different representation is actually the same exact one, because each of these tells you that C1 is the same as D1, C2 is the same as D2, and CK is the same as DK. Right? So the representation is, or let's say, must be unique. Okay. Right. So what this means is that since this is unique, we can use it to represent our vector in a way that is going to give us a coordinate system, right? So we're just going to take this representation that we have in terms of those basis vectors and use the constants that we get as our coordinates. So how we'll represent this is if X, so I'm just copying down this thing we have up here, but if X is equal to this guy, CK times VK, like this, then the constants C1 up to CK are going to be the coordinates of X in the basis B, right? So it's really important that you make it clear that B is the basis that you're representing your coordinates in, and then the B coordinate vector of x is going to be just the vector where we just plug in those coordinates. So this is how we're going to represent the coordinate vector of x in the basis B. So we'll put brackets around it. So we have our vector, we put brackets around it and a B as a subscript so that we know that this representation is not like our standard representation in the standard coordinates. When we use standard coordinates, we don't have to append anything like this. But what this will be is, again, just the vector of those C1, C2, up to CK, like that. So notice it does matter the order of your vectors in your basis, right? So you just need to be consistent with that. Like we labeled them V1, V2, VK, and then we ordered the coordinates by those labels. So it does matter. Okay. So let's do an example where we take a basis and a vector. So we take a basis for a subspace, a vector in that subspace, and we represent it using these coordinates. So I'll just do this down here. So say our basis is going to be these two vectors. So this will be V1 is 1, 0, minus 1, and V2 is 2, minus 1, 1. So our subspace will just be the span of these. Okay, then clearly we already have the first condition for this being a basis for H because we just defined it that way. And also, these are linearly independent because one is not a multiple of the other, right? So when we have two vectors, it's not so hard to check linear independence because we just need to check that we don't have one as a multiple of the other, right? Oh. Oops, wrong word. There. Okay, Veronica, you had a question?
Yeah, I think I figured it out though. So,
Okay.
sorry.
Okay. No problem at all. Okay, so we have these two things, meaning that if we take B to be the collection of these two vectors, V1 and V2, this is a basis for H, right? Okay. Now consider a vector X. So say this is our vector X, and we want to ask, so our question is this in H, first of all? So is X in H, and if so, represent, or let's just put it this way, find the B coordinate vector of X, right? Okay. So how do we figure out whether X is in the subspace H?
We set up an augmented matrix.
Yes, we set up an augmented matrix. So we just put V1 and V2 in the first two columns, augment with X, and we see if this is consistent, right? Now, this is gonna be 1, 0, -1, and 2, -1, 1. And then X is 4, -1. Wait, sorry, this should be a -1. There we go. Okay, 4, -1, -1. Yeah. Okay. So, to row reduce, we just need to take row 3, replace with row 3 plus row 1. And that will give us 0. I'm also at the same time going to multiply row 2 by -1 so that we just get 1s here. And then in the last row, we get 0, 3, and 4 -1, so also 3. Great. So we have that row 3 is a multiple of row 2, so we can just eliminate it. So we get, this is our row echelon form, right? And I guess we can go one step more and get reduced row echelon form by taking row 1 to row 1 minus 2 times row 2. So 1, 0, 0, we'll get 0, 1, 0. And let's see, that will be 2. Right? Yeah. Okay. So what this tells us is that if we were to set up an equation like C1 times V1 plus C2 times V2 equals X, that our solution would be solution would be C1 equals 2 and C2 equals 1. Right? Okay. And since we have these constants that give us this linear combination for X in terms of V1 and V2, that means that those will form our coordinates for the basis. So in this basis, the representation for X is 2, 1.
What is this notation? What is that?
This part right here,
Yeah.
this is the B coordinate vector.
Can you explain that concept a little bit more? Because I got kind of lost there. What is the
Yeah.
coordinate?
Okay, so the idea is that you want to represent X using coordinates, right? C1 and C2. Or okay, just generally, you want to represent X as a linear combination of V1 and V2.
Yeah.
Okay, so when you figure out what C1 and C2 should be, in our case, it was, we got 2 times V1 plus 1 times V2, right? This representation in terms of V1 and V2 is unique. So we can, basically this is like a shorthand for writing B as a linear combination of our basis, right? So it tells us that if we want to write down X as a linear combination of vectors in B, that we use the constants 2 and 1 to do that.
I have a question. So if you were working, say you were using the, it's called the standard basis for Rn. Would the XB in that case be exactly equal to X itself?
Okay, so are you talking about like in terms of this problem, or are you talking about in terms of?
No, this is just like something for when we were talking about before about the standard basis for Rn.
Yeah. So given a vector in Rn, so it has okay, so say it has coordinates C1, C2 up to Cn, then the standard basis, remember, is E1 up to En, and these numbers give you the representation. So C1 times E1 plus C2 times E2 plus Cn times En, right?
Cool. So then if you were to write x, that thing where it's x inside brackets with the subscript v,
Mhm.
The v coordinate vector of x is just x.
Yeah, exactly. It's just this thing.
Cool.
Yeah, in terms of that basis. But usually when we do the standard basis, we don't include the b.
Oh, you don't include that little v?
Not if we're using the standard basis, because we sort of already have, like when we write down a vector in this way, we're assuming we're using the standard basis. Right. So just to keep it like separate from this representation in terms of other vectors.
Oh, whoa, my head hurts. So like all this time when we've been writing something as x,
Mm-hmm.
that is a way of writing it as x of v just for the standard basis.
Yeah, it is.
Whoa, weird.
Yeah. Okay,
Is
so
there a way to, sorry, just a quick question. Is there a way to visualize B graphically, or is that the wrong way to think about this?
definitely there is. So there's this picture in the textbook that I sort of just pasted in here. Right, so it's this page 156. And there's, so imagine this green part is your subspace. So it's sort of a plane in R3, right? And you have your two spanning vectors, which are these blue, maybe I'll highlight them right here. So this is V2, this is V1. You see that? Okay, so those are your two spanning vectors. And then a vector X that sits inside of here, so this is X right here, is written as a linear combination of those two. And you can see that this sort of forms a grid on your subspace. Okay, 3 blue, 1 brown. Yeah, definitely. I do recommend that YouTube channel. They do make really good videos. So yeah. Okay, so yeah, this is a way to visualize this. And you might remember that back in when we started talking about linear combinations of vectors, we had this idea of like creating a grid from the two vectors. And there were some pictures in the textbook where we had these two vectors and we like created a grid that showed us like how to write things as linear combinations of those two vectors. And you may have had a homework problem on this, I believe. Right? Do you guys remember that? So it's a similar idea. All you're doing is writing X as a linear combination of those basis vectors, right? But then it's nice to be able to just sort of like, we're sort of abstracting away the basis vectors and just writing them as a coordinate, right? Okay.
So when you write that the x with the little basis, so that is saying how to map x on the coordinate system of the plane H, like for this given example.
Yeah, exactly. Yeah. So just looking at this right here for this particular X that they've written. So here X is 2 times V1 plus 3 times V2. The coordinates of X in terms of this basis are going to be 2, 3. Right?
So the origin of the basis is always the same. It's just kind of the orientation that changes. Okay.
Yeah, exactly. Yeah. And so remember we talked about this example with R2 where we had one basis was just the standard basis 0, 1, 1, 0, 0, 1. And so these give you your coordinates, right? Your standard coordinates. So you can imagine your grid looks like this. You can also represent, we should make these. Okay. You can also represent R2 with a basis using, like I said, this was, we could use 1, 0 and 1, 1. And then 1, 0. So that's this guy right here, and 1, 1 would be this vector right here. So instead of getting like your standard coordinates, you get this slanted grid, which you can still use to represent any point or any vector, right?
So in the image from the textbook, it's just shown as a little square for like a visual representation, and the plane actually continues on all directions, right?
Yeah.
Okay, phew. Want to make sure I was understanding it properly.
Yeah. So when you're representing a subspace, you sort of have to have edges or else you can't see the thing. It's just like, I don't know, a limitation of like our visual abilities. So this, maybe if you have some kind of like 3D representation, it's a little bit easier. But yeah, so this is, yeah, how you can picture it. And this is the idea of representing a vector in terms of a given basis. Okay, so there are some definitions I want to get through, and then at some point we're going to do the quiz. Is that right? What time?
What's the quiz going to be on?
The quiz is on like inverses of matrices and invertible transformations. Okay. So there are some definitions that will be relevant. The first one is going to be the dimension of a subspace. So I mentioned this in the beginning, and we're sort of utilizing this idea that the number of vectors in a basis is always going to be the same, even though we could have many different bases for a given subspace, right? So, so the number of vectors that appear in a basis is going to tell us the dimension, right? And this actually corresponds nicely with our intuition for dimension. So the dimension of a subspace, H, is the number of vectors let's see, in a basis for H. And this thing, the dimension, will be denoted with the dim of H. Okay. And by convention, the dimension of the, so the dimension of the zero subspace, the one that only contains the zero vector, is going to be 0. Okay, which, you know, corresponds with our idea that like a point has 0 dimension, right? Okay. So, yeah, we have this idea, and then of course there's this special subspace that we talked about last time, which is the column space. I guess we also mentioned it today. And so it gets its own special name for the dimension of the column space. So the rank of a matrix A, it refers to the dimension of the column space. So this is the dimension of the column space, let me put it this way, of the column space of A and it is denoted rank of A, like that. Okay, so we can think of this is right the size of the column space. It's also, if you want to think about this in terms of linear transformations, so remember for every matrix we have an associated linear transformation. It will be the dimension of the range or image under or of the associated linear transformation. So this is where we take A times the variable X. Okay. And then there's one more thing. I think this is not defined in the textbook, at least I couldn't find it. So I'm going to define it this way and refer to it this way, but you might not see it in the textbook. And this is called the nullity. And as you might guess, the nullity of a matrix A is the dimension of the null space. Okay? So nullity of a matrix A is the dimension of the null space of A. And we denote this, fortunately, there's not like a nice way to abbreviate this without, having some redundancy with null space. So we just write out nullity of A. Okay.
It's the dimension of the void.
Oh, sorry.
Sorry.
Yeah. So what were you saying, Bo?
I just said it's the dimension of the void.
Of the void? I've never heard it referred to as that, but yeah, sure.
I was making a joke.
Oh, okay, I see. Yeah. There you go. Yeah, that's how to think about it. Okay, wait, did you have a question, Veronica?
Yeah, I'm trying to figure out what's going on with the rank of the matrix A. So I get that it's the dimension of the column space of A, but I'm confused about why that makes it the dimension of the range of A of X, or A times X.
It is because of this connection between the column space and the range of the linear transformation. So maybe if you refer to like the, let's see, invertible matrix theorem that we had, let me see if I can find it and maybe pull it up.
Because I feel like you can have situations where your matrix A only has like 2 pivot columns, but then the image of T of X might not be in R2.
It might not be in R2, but it will lie inside a subspace of dimension 2.
Oh, okay. Sorry, my bad. Thank you.
Yeah, no problem. Okay. Right. Okay, so to say a little bit more about the rank and nullity. So rank refers to the dimension of the column space. So the dimension of, we'll just write it this way, the column space of A, which we remember is the number of pivot columns of A. So remembering that when we found the basis for the column space, we just row reduced and took only the pivot columns, right? So the dimension is going to be the number of pivot columns, right? Okay, so that's the rank, and the nullity. So here's is the dimension of the null space of A, right? And this is equal to the number of free variables, right? So remember, when we're finding the null space, we would write our solution in terms of the free variables and create a parametric. So when we write out the parametric vector form, we get those vectors that span the null space. And the number of vectors that we get would depend on how many free variables we have, right? So the dimension of the null space of A corresponds to the number of free variables. And that is the same as the number of columns without pivots, right?
So the rank of the matrix is the same as the number of pivots.
Yes, exactly. Okay, so just looking at this, we have the rank is the number of pivots, or the number of pivot columns, and the nullity is the number of columns without pivots. So if we add those two things together, we should get the number of columns of A, right? Because a pivot, either a column either has a pivot or does not have a pivot, right? So the rank plus the nullity is the number of pivot columns, or let me put it this way, number of columns with pivots plus the number of columns without pivots, which should just equal the total number of columns of A, right? So this is what is called the rank nullity theorem, right? So the rank nullity theorem, or I guess, well, rank theorem, I'll probably, so the textbook calls it the rank theorem, I'll probably call it the rank nullity theorem, just out of habit, but it says basically that if A has n columns, then the rank of, whoops, then the rank of A plus the nullity of A is equal to n. And it's really for this reason that we just said. Okay, so that covers rank and nullity. Let's see, how are we doing on time? Should probably, wait, so 35, 45, 50. Okay, I should let you get started on the quiz probably. Okay, so next time we will have a little bit more to cover in section, so this is section 2.9, and then we're going to move on to determinants, which is 3.1. Okay, so I need to